our speaker today is Kelli Moran. Kelli Moran earned her MS in geology from East Carolina University in 2012, where her research focused on environmental reconstructions of a barrier island system along the North Carolina coast. She worked briefly for an environmental consulting firm in St. Paul, Minnesota, and she successfully defended her dissertation at LSU in the Department of Oceanography and Coastal Sciences in December of 2022. Kelli's research is largely tied together by the use of geophysical instruments, sidescan, bathymetry, and subbottom, and focuses on how sediments move and deposit on the coasts over a variety of geologic influences. During her time at LSU, she's led several field expeditions for both fiber coring and geophysical survey. First publication from her dissertation was released in October of 2022, and two other publications from her dissertation research are forthcoming. She was recently selected to attend an NSF-funded international research experience in the Netherlands, where participants learned the latest in Delft 3D modeling. She was also awarded the NSF GSA Robert K. Fonstock Award in 2022, the American Association of University Women Eleanor Earl Memorial Scholarship in 2021, and the Hydrographic Society of America Southeast Chapter Scholarship in 2020. So please join me in welcoming Kelli.
Hello, everyone. It's nice to be here. I am going to be talking a little bit about one aspect of the research that I did while a graduate student at LSU. I understand that this is kind of a mixed group of engineers, oceanographers, maybe some geological oceanographers. So at any point I'm not making any sense or, you know, everyone's eyes have glazed over, I'll try and explain a little better. So please feel free to, I don't know, give me confused faces if you need to. So I will be talking about the contrasting modes of sediment infilling and geomorphic change within a sand-dominated dredge pit on the inner Louisiana shelf. Something that we'll just start. So again, this is work I did at LSU, but to give you a little bit background on myself, or not. I got an undergrad in geology at Kutztown University, which is a small Pennsylvania college that is not related to the ocean in any way. I then went to East Carolina University. I got a master's in geological sciences. That's much more related to the ocean. That's kind of where I fell in love with kind of coastal mapping and geophysics. Again, I went and took some time off and eventually wound up back at Louisiana State University, where I got a PhD in geological oceanography. So just kind of to give you an idea of where I'm coming from, kind of more on the geological side of things. What I've learned is every time I go to a geology department, they're like, you do stuff that's way too recent, 10,000 years is nothing. And then I go to an oceanography department and everyone's like, 10,000 years, what are you, crazy? That's a long time. So I'm trying to play kind of that middle ground of geology, modern oceanography, and how those interplay. So my research focus in general explores the mechanisms driving sediment transport and deposition on the continental shelf. And it's tied together by a thematic focus on geomorphic change and sediment transport and those implications that those types of things pose towards problems like sea level rise and climate change as we move forward. Can everyone hear me?
Yeah.
I'm loud. All right, so most of my research is tied around geophysical survey. So we talked about a quick list of things that I kind of use, like tools that I use in my research. I'm going to give you kind of a breakdown about how I think about them and how I use them in my research. So geophysical survey takes a lot of time to get set up. It's a lot of wiring boats and running antennas and making sure everything's communicating, but not communicating too much because you don't want them to communicate with each other. It's a bunch of different sensors, but once you've got it all set up and you've done climbing all through the rigging of the boat, then you just sit on a boat and you zigzag back and forth and you mow the lawn. So it's highly engaging and then highly boring all at the same time. So I use three different types of kind of sensors in my research. Specifically this project, I'm going to talk about all three, so we're going to go through all three. One of those types of sensors is called sidescan sonar. Basically, it's going to use sound, it's going to travel through the water column, and it's going to reflect back based on intensity difference between what's going on the sediment floor. So a lot of people, when they think of side scan, they think of mapping, right? You get things like this, where you get a very clear image, intensity differences bouncing back off of what's on the seafloor, and you get to map images on the seafloor, which is really highly useful. You can also use it to map features on the seafloor, like sediment texture differences. So we're going to be talking about that a little bit in this particular project. This image is actually from another project that I've done. And those are large scale sand waves in kind of a muddy dune system. So you can get at some very interesting, complicated geologic features on the seafloor with sidescan. Another tool that I used for this project is bathymetry. You can think of bathymetry a couple different ways, but basically you have a sensor on a fixed point with lots of GPS antennae attached to it, so you can get an exact location and an exact depth, and you can calculate out how far you are from the seafloor. So you can think of it as a measurement of the water column, or you can also think of it as kind of building a topographic map for the seafloor. So that type of data looks like this. You go and you collect it. Those horizontal lines are actually striping from the different seismic lines you collected. And then you get areas where you have topographic highs. In this instance of this particular figure, the warm colors are topographic highs or ridges. The cool colors, those deep blues, are topographic lows. And you can kind of get an idea of what the seafloor looks like in relief. You can also take that one step further and project that image into 3D space and get an exaggerated view of exactly what you're looking at. So this particular image, I'm a very, very visual person. And so this is actually the first survey of the dredge pit we're going to be talking about later, projected into 3D space. So you can see that, yeah, we've got a nice hole, but it's not smooth on the bottom. There's a lot of topography going on in there. So in some instances, these types of visuals are very helpful, and sometimes maybe not so much. The last type of tool that we're going to be using for this particular project is subbottom. Subbottom is a little harder for most people to understand. You can picture a topographic map, you can picture something on the seafloor and understand it. Subbottom uses sound, and it travels through the water column, and then the hydrophones or the sensors kind of listen for how quickly that sound comes back. And based on the time travel, the time of travel for the sound wave to go down and bounce back, in bounce off of density differences, you can get what's going on below the sediment water interface. So the top images are all 3 different types of chirp systems or subbottom systems. This bottom image is actually a seismic line. So if you were to take the seafloor and cut it and look at it like the layers of a cake, this is what you would see. This top section here, this kind of staticky looking section, is actually the sediment, or I'm sorry, the water column. So that's just the water column. And then this dark line that runs all the way across the entire image is actually the sediment water interface. So you've got a pretty good density difference between sediment and the water column. And then every unit that you see below that dark line is a difference in sediment density. So the difference between sands and muds would be very obvious, but the difference between a couple different mud layers wouldn't be as obvious. This particular image is actually of a dredge pit that's infilled completely. So this kind of dark line that runs across the bottom of the image is actually the dredged pit bottom. And then all of those kind of half moon lines are actually different units that have infilled that dredge pit over time. Does that make sense to everybody? So those are the 3 types of tools that we're going to be using to kind of interrogate this dredge pit off of Louisiana's coast. Before I get too crazy into that, I want to give you some background into Louisiana. It's a little bit different than here, but some important information for you to kind of have working in the back of your head is that the Mississippi Delta has moved, migrated, and built several delta complexes over time, going back a few thousand years. So basically what this means is the delta system builds out, you build land, you've got everything stable and secure. And then as the river system, oops, sorry about that. As the river system, takes up all of its accommodation space, it winds up abandoning a delta lobe and moving somewhere else. And then you have kind of a collapse of that delta system over time. So the easiest way to kind of show you this, I'll get to that in just a second. This nice white square is the location of the dredge pit we're going to be talking about. So it's on the kind of edge of 2 of those abandoned delta systems that are no longer active. Something to keep in mind when we keep going through. This is an early model of delta collapse and kind of what happens once the delta system is abandoned. So this was first published in 85 by Penland. But it's still a very important, very reasonable thing to apply to the Mississippi Delta system. Basically, you're going to start in the top left corner up there with the nice active delta. The delta lobe is abandoned. The river system moves further away. For whatever reason, you've taken up accommodation space, sea level dropped, what have you. The delta's been abandoned. As you move through time, you're no longer producing or storing sediment in that system. The muds and things that had started to build that marshy system start to compact, collapse over time. You start to get erosion, and you get a kind of bay head delta system of barrier islands flanking that original system. So you get ocean reworking, and you're building nice clean quartz sand beaches of reworked sediment along the outside of that delta. As everything continues to collapse and be reworked, you wind up with what you want in a nice coastal system, a nice barrier island arc, right? Barrier islands are going to protect that kind of marshy system behind it and long-term protect that delta system. Unfortunately, if it collapses far enough, either sea level rise takes over or the delta continues to subside, you eventually wind up with a submarine shoal. And submarine shoal is actually where we're going to start with the dredge pit today. So Ship Shoal is a submarine shoal. Oh, I moved around my slides. So Ship Shoal is a submarine shoal that we're going to be talking about that our dredge pit was excavated in today. Some more information on Louisiana. So it's important to know that this type of model was described in '85, right? That's been around a hot minute. And Louisiana is constantly losing coastal systems, right? The concept of land loss, sea level rise, and coastal change has been around in Louisiana for a long time. It's something that the coastal communities have taken an active stance on and have started to try and mitigate some of that land loss. So some other areas like Florida have pretended like sea level rise and climate change aren't a thing, and they're starting to see the consequences of that. Louisiana was like, oh goodness, this is all going under, we're in a lot of trouble. So they started something called the Coastal Master Plan as part of the Coastal Protection and Restoration Authority. So every 5 years, they have all of the coastal geologists, ecologists, biologists, everyone they can get together and come up with a master plan for trying to preserve and protect the coast. Now I know that this isn't very easy to see. This is taken right out of the Coastal Master Plan. If you're interested in it, it's very easy to come up with online, or I can give you a link. This is the 2023 Coastal Master Plan. And what I wanted you to see is all of the areas in blue are the areas of land loss for the next 50 years if the minimal amount of sea level rise or coastal change happens. So all of that blue is what's lost in the next 50 years if the minimal amount happens. This is what happens if the maximum amount happens. So all of those blue areas, they're not just marshes, they're not just, out there doing nothing. Those are homes, those are people's houses. A lot of people live in those coastal communities, and if nothing changes and no one tries to fix things in the next 50 years, Louisiana expects to lose all of this coast. With that being said, Louisiana spent a lot of time and a lot of money trying to fix their problem, trying to engineer themselves out of this problem. They've put a lot of money into projects like barrier island reconstruction projects, right? Those barrier islands protect our marshes, therefore we don't lose them. They've done a lot of sediment diversion projects where they actually take out portions of the levee system for the Mississippi to try and get sediment into areas and start building new land in areas that would have normally gotten sediment from the Mississippi. So they're kind of working towards engineering themselves out of this future. That gets us to dredge pits. So part of this long-term plan, this coastal restoration plan is, again, barrier island restoration projects and trying to keep ourselves from completely flooding. Now, the other side of that is, if we dig a bunch of holes offshore, what does that do? Does it cause other problems that we didn't foresee? Or does it not really matter that much? So this particular project that I got involved in is basically trying to map and determine what the possible implications of using dredge pits offshore could be moving forward. So before they even got started on this particular project, they spent a lot of money and time trying to model what they thought putting a dredge pit on Ship Shoal would do. So they did a really, really great study and model, one-dimensional kind of model, trying to say, okay, what type of environment do we have? What type of sedimentation do we have? What can we expect to change over time? And what does that mean for a specific shape of dredge pit? How quickly do you think it'll infill? What does that mean for the coastal community? Things like that. And then they realized, well, models are great. They're really helpful and they're good for the planning process, but how do we know if that's real? Like, how do we ground truth that? So that's where this project kind of came along. We were talking about kind of that coastal shoal system, right? So at the very end stage of that delta system, we have that submarine shoal. Ship Shoal, which is going to be in this nice green image here, is a collapsed barrier island system. So it's almost clean quartz sand. It was a beach system at one point. It makes it an ideal place to go get sand and put on a modern beach, right? It's exactly what it was. It's relatively close to the coast because it was a beach system close to the coast. So it's ticking a lot of boxes. It's a really ideal location. When this project was first kind of proposed, it was the first dredge pit on this beach, but Louisiana had done a couple of different other projects kind of around the area. Since this particular project was done, so we're talking about block 88. Sorry about that, guys. It's going to be this nice kind of rectangular system right there in the middle of Ship Shoal. Since then, they've gone and excavated Caminata Borrow Pit, which is significantly larger. So anyways, Ship Shoal is one of the larger borrow areas in the coast. They're planning to continue to excavate it. And so this project was looking at kind of how accurate we were with our modeling and if that continues to be a reasonable place to collect sediments. So in 2018, 8.4 million cubic meters of quartz sand was excavated for the Whiskey Island Headland Restoration Project. And as I said, early modeling predicted that this particular site would infill pretty quickly within 3 to 5 years, meaning that potentially that would not impact the coastal system at all. So this project was started in 2018, and in 2019 and 2020, repeat bathymetric, side scan, and subbottom surveys were collected to kind of quantify change over time. And something I just want to point out so that it'll come in handy later is that the longshore current direction is from the east towards the west. So it's kind of moving across that shoal system. So, because all of these types of data kind of feed into each other, this gets a little complicated to explain. I'm going to do my best, but please feel free to ask questions if you have them. First maps I have up here are bathymetric maps. So they're showing you again kind of the topography of the seafloor over time. Warm colors, those browns are going to be topographic highs. So the top of that shoal system. Cool colors, those blues, are going to be topographic lows, so excavation into the pit. On the far left, we have the initial dredge pit area. So the survey was conducted immediately following dredging so that the dredging company could take it and say, look, we did exactly what we said we were going to do. We removed the sediment we were going to remove, and it is in the shape and design that you guys suggested. In that first image, that 2018 image, you can see that there's a lot of variation in kind of the texture of the seafloor. You can see that there are some areas that are a lot deeper, some areas that are a lot shallower. You can also see pretty clearly some kind of hopper dredge scoop marks. You can see exactly what type of material or exactly how they removed material. In the 2019 data, as you kind of move through time, things have smoothed out. You've got a lot less topography going on, and things are kind of being a lot more kind of homogeneous. And then you get into the 2020 data, and you start to see some interesting features developing in the dredge pit, like slump features and depressions. So you're kind of seeing change over time. And we're going to get into the nitty gritty of this, but I kind of wanted you to see that the dredge pit makes a lot of sense. It starts out with a lot of topography. It starts to accumulate sediment, smooth out, things smooth out and change over time. All right, so as I showed you guys earlier, this is kind of the general shape of the dredge pit. That black line is going to show up through all of my images. So every time you see that, that is the shape of the original dredge pit and the edges of that original dredge pit. Side scan data. So we talked about side scan data and how you can kind of use it to get at textural differences of the seafloor, right? So I'm going to convince you of that. This particular project, we collected side scan data, and we also collected sediment cores. So I have 5 locations mapped here. Those are 5 sediment cores that we collected. If you notice, I have 2 of them on kind of that nice yellowish color, and then I have 3 of them on that kind of dark brownish color. All right, so if we go and look at the side scan data and the sediment core data, and we look at the grain size, that yellow color is tied to sands. So the sample that's kind of in the middle of that dredge pit with that kind of yellowish color is going to be the red line on my grain size analysis. All right, so it's got a lot more sand in it than some of the other ones, but it's not completely sand. The sample that's completely out of the dredge pit, which we would expect to be almost clean quartz sand, is in fact almost clean quartz sand. It's that nice green sample. All right, so you can see that you're seeing 2 different sediments, but generally speaking, the higher reflectivity, that yellower color, is going to be sand. And then, the remaining 3 cores, cores 1, 2, and 3, which are kind of more in this silt clay area, are going to be those darker muddy areas. All right, so now we've got that connection. We can go back and we can look at the side scan data, and we can see that between the 2019 and the 2021 survey, or 2020 surveys, so a year apart, we've got mud infilling this dredge pit. All right, it mostly accumulates in those low-lying areas that we saw in that initial dredge survey. So it accumulates in the middle and in the northwest. And then as time carries on and we collect more sediments, it accumulates kind of in the other low-lying areas. Everyone's good with that? So we're accumulating muds. Another way we can go ahead and play with this is we can also start to see some interesting depressions and features on this, right? So we've got kind of uniform mud accumulating in the low-lying areas. Then we've got some weird things going on in 2021 data. We've got bottleneck slides up in the northeast section where we've got collapse features. Those types of features happen when you have an unconsolidated mud hits a trigger point. It could be a change in pressure, it could be a change in velocity, and those create collapse features. We also have some interesting kind of pitting and dimpling here in our mud areas that we also see in our bathymetry. So we have some interesting collapse or depression features there as well. So that was really driving me nuts. We had not seen collapse features in dredge pits before. We have them, they're kind of slumping at the sides of the dredge pit. It makes sense. You're going to dig a hole into sand, the sand's going to slide into the bottom of the hole. But we don't see collapse features like this all that much. And then I remembered that hurricanes love Louisiana. So in 2019, during that first survey, we had one hurricane go through. It's Barry, it's that black line. That's vaguely near the research area that we were in. But then 2020 happened, and every hurricane that entered the Gulf made a beeline for Louisiana. And all 5 of these hurricanes happened in one season in the Gulf. Turns out, I wound up with a hurricane study and I didn't even need to. So the hurricanes greatly impacted the way that sediment was moving and transporting into this dredge pit. So it makes things complicated. Did the model predict hurricanes would be crazy and make sure that the dredge pit fell a certain way? Probably not. Can I compare my data now to that model and still have a reasonable result? I don't know. But a lot of interesting things happened with this hurricane season that kind of are going to keep showing up in this interpretation of the data. So, as I promised, we have kind of these weird depression features that are happening in the side scan data. We can see because they're infilling with mud, but you can also see them on the bathymetry. So there's topography going on. It's not just that we've got these weird patches of mud accumulating that I can't explain. It's also created some interesting topography and depressions. We see the same thing with the bottleneck slides. You can see them on the bathymetry, although it doesn't look like it's great on this screen, so I'm sorry about that. So hurricanes are playing a large role in Louisiana's kind of change over time. So we've talked a little bit about how the bathymetry is showing us change. We talked a little bit about the side scan data and what that means about our infilling. Now let's get into the subbottom data. So this is kind of a little bit of extra bonusy things. This is the type of thing that really interests me, so we're going to talk about it. Our subbottom line runs right down the middle from north to south through that initial survey area. So you can see that on that map there, A to A prime. So the far side is the north, this ends the south. The top panel is the 2019 data, and the bottom panel is the 2020 data. So it's the exact same line, same orientation, right through the middle of the survey area. Again, that kind of static-y area above that dark line is going to be the water column. So with that, we can look at how much the pit wall edges have changed over time, because we can quantify. This doesn't look anything like that, right? We had a nice crisp edge of our pit wall. It's collapsed into the bottom of our pit here. We also have some interesting things going on with this. This type of noise in the data is called, can be associated with biogenic gas. Basically, when you have organic rich muds deposited in your seafloor or in your sediment, get critters munching on the mud, breaking things down and generating gas. And gas attenuates the sound signal that we're using to interpret what's going on below the sediment water interface. So another side of this, not only can I show you that the pit walls have collapsed and changed over time, I can also show you that in 2020, we had a lot more muds and therefore biogenic gas and therefore muds accumulating in the bottom of the dredge pit over time. Everyone's believing me? So now that I've showed you that the pit walls have collapsed a little bit, here's a better representation over time of how the edges of the dredge pit have changed. So these are slope maps. Basically what I did was put it in MATLAB and said, show me the slope above a certain amount and show me a slope below a certain amount. So that nice red color is going to be a slope of about 20 degrees. And the yellow, or the orange color is going to be 0. So you can see in the 2018 data, we have nice crisp edges to our dredge pit. We have a lot of texture going on in that middle of that dredge pit. In 2019, we've got a little bit less stable pit wall edges. We saw that they were kind of still easy to identify on the subbottom data. But by 2020, the dredge pit's walls are really starting to collapse. We've got things kind of smoothing out altogether. And the difference between the 2018 to 19 data and the 2019 to 2020 data, really that changes those hurricanes, right? We've got a lot more wave base impacting the shelf or the shoal area and it's causing a lot more change in our dredge pit in those 2 years. So we do see some interesting things. We're going to talk about them in a second. We do see kind of a westward migration of the northwest portion of this dredge pit. So you can see that things kind of look like they're smeared. I went through like 6 million different ways to try and figure out if that's something I did by accident with the computer. That's real. And then we also have some interesting things. We were showing you those depressions on the bathymetry and the side scan, and we're also seeing them in the slope map. These things are kind of creating these dimpled hole features. So now I'm going to show you a cross section straight across the slope map. So let's get into the nitty gritty, the specifics of infilling. So the 2018 data, so basically for these figures, I went and traced the slope map across the dredge pit and generated these lines. So the blue is the 2018, the orange is the 2019, and the green is the 2020. All right, so when you just kind of look at these maps, this is straight across the middle of the dredge pit. We can see that we have erosion on the western side of the dredge pit. That's the area where I showed you that the dredge pit started to kind of smear to the side. So we've got erosion going on there. We can see from the blue to the green, there's a decent amount of change on that western side. We can also see that we've got deposition on the eastern side, which kind of took me by surprise. I didn't quite expect to see deposition of any sort on the eastern side without some sort of collapse into the pit. We also see the obvious deposition at the bottom, right? We had a topography surface that's basically been smoothed out now. But what types of infilling are we seeing with these? So we've got pit wall collapse, right? So we've got the edge of our dredge pit. It's no longer stable. We've got the angle of repose has been a little too high and that has slumped into the bottom of the dredge pit. We've got some infilling at the bottom of the dredge pit from that. We have bed load transport. That's the only way that I can come up with that reasonably explains why we would have sediment accumulation on the eastern pit wall edge. At the very beginning, I told you that sediment transport was from an east to a west across the dredge pit. And so what I think is happening here is we're basically having the shoal itself kind of migrate towards land, towards towards northwest, and accumulating sediment on the edge of this pit wall. So right, so we've got bed load transport, we're migrating and we're kind of collecting on the leeward side of that pit wall. And then we also have suspended load being deposited in the bottom of the dredge pit. Again, that makes sense. We've got sediment kind of being moved from the Mississippi with longshore current over the dredge pit and slowly accumulating in the bottom of that dredge pit as you increase the water column and the velocity drops out. Everyone with me on that? Okay. So now how do I get at infilling rates? The easiest way to get at an infilling rate for the bottom of the dredge pit is to use beryllium-7. So beryllium-7 is a tracer that you can use for it's got a very short half-life, and it's going to allow you to get at basically short-term infilling rates and kind of punctuation of those infilling rates. So with the beryllium-7, we're able to look at the kind of we're able to look at the trends in the way those beryllium markers are going down core, and we're able to determine that between 10 to 12 centimeters of river-derived materials are being deposited within about a 6-month period. We're also able to tell that this is a punctuated delivery, or there's a lot of bioturbation. From what I was able to see with the sediment cores, I don't think it was bioturbation, but I can't completely rule that out. So we're getting kind of a punctuated delivery of muds from Mississippi into the bottom of the dredge pit. And with some quick math for that, you're able to come up with a sedimentation rate over time. Okay. So this is a lot of information in one image. So the top 3 images are the bathymetry maps I've been showing you the whole time. I've got 2018, 2019, and 2020. The bottom 3 panels are difference of depth maps. So I've taken those individual panels and I've done some raster math, and I've been able to say, okay, between 2018 and 2019, if I subtract 18 from 19, this is the change that we see. Okay, so areas that are green are going to be deposition, and areas that are dark brown are going to be erosion. I've done the same thing with 2019 to 2020, and then I've done 2018 to 2020. So you can see that things changed a little bit in 2018 to 2019. We've got a bigger change between 2019 and 2020, where I'm saying the hurricanes happened, right? They made major changes happen. We've got lots of erosion. We've got deposition in some interesting areas. But I think the easiest way to look at this is the whole change over time for the entire dredge pit, right? So that's that kind of cross section I showed you with pit wall collapse and things. So we're able to, again, determine an infilling rate based on our beryllium-7 of 0.2 to 0.25 meters per year of sediment infilling, just on the bottom. All right, so that's this green area kind of in the middle. That's that muddy sediment. But what really interested me was this really bright green line on the side. If you look back at the side scan data, that's all sand. All right, that's clean quartz sand that's been moved with bed load into the dredge pit. So if I do some quick math for, the volume of sediment being accumulated kind of in the bottom of the dredge pit over those 2 years is about 438,000 cubic meters of mud being deposited in the bottom of the dredge pit, which is a lot of mud. But back to my sand, I'm very excited about the sand. If you do some quick calculations for the sand, you come up with 102,000 cubic meters of sand being accumulated on that dredge pit edge. So what does that mean? Why am I excited about that? Basically what it means is it might be possible to engineer dredge pits on this shoal to accumulate sediment and basically be reusable. If you can engineer the shapes of these dredge pits in orientation with longshore current and pick a location on those shoals that are a little closer to the wave base and something that's going to be impacted a little more regularly, then it may be possible to engineer these dredge pits so that we can continue to use them for sediment resources for ongoing problems with Louisiana's coast. So those are kind of my big takeaways from this particular project is there's a lot to be done. There's a lot I learned about the way that the original model was developed and ways to improve that model moving forward that I think future projects should take into consideration when trying to determine and develop dredge pits in the area. The sedimentation rate that they gave of 0.86 meters per year is significantly higher than what we were able to calculate and find. And I think that that is even a high number for us, simply based on the fact that we had those hurricanes really stirring up the Gulf. So there's some things to consider with kind of moving forward, but I think that the major takeaway is Louisiana could potentially be able to engineer itself into a better standing with types of projects like this. But if you're really, really interested and your eyes didn't glaze over too much, this is published. You can absolutely have a copy of this. Just send me an email. I would be happy to send you this. That's my email. This was published 2 years ago now. And so there's a lot more information about the model and the different parameters that went into that and kind of the nitty-gritty details. But that's definitely available. And then of course, you got to thank your funding. So BOEM funded this project, which is awesome. And just because I could, geophysics works takes a lot of people and a lot of time and a lot of patience. And everyone here put a lot of effort into the research that I just showed you. So yeah, I'm here talking to you, but there's a lot of people behind the scenes. All right, any questions? There's a lot of information, yes.
With what you're doing, you're looking at just kind of gross infill rates, you know, kind of an average, and there's good reasons for doing that. But if you're really doing planning, you know, trying to use it as coastal planning, hurricanes are a reality of life, and they come from different directions. They have different strengths. There's different sediment types. Is there any thought to taking this, potentially combining with other databases, so that you can start characterizing the amount of infilling based on how strong and how recent the most recent hurricane was, or the direction it came from, or trying to get more than just an average filling rate, trying to figure out where and how fast?
Right. So turns out my whole dissertation was there was a hurricane. This turned out to be really cool. So in this particular project, there was no interest from our funding sources to kind of work in that direction. I'm still working on BOEM to try and poke them in that direction. But I have another project, which is specifically, it's specifically looking at sediment volumes eroded as a result of a hurricane, because I had opportunistic repeat bathymetric subbottom sidescan surveys. So it's something that I am definitely working towards trying to quantify those things. But it's, like you said, a hurricane. I mean, the hurricanes I showed you, the eye of Laura's hurricane was almost 80 meters wide. So that's like most, where is Laura? Laura is the pink one. So Laura would have impacted like all the way out here, like with no effort whatsoever. So it's very hard to quantify. There's so many variables, right? There's how big it is, how much wave base it creates. So the answer is I can't get anyone to be interested in that, but they should be. And this was a wild year. This year, we had to leave our house like 3 times, and there was no power. Parts of Homa are just completely destroyed. You would think Louisiana would be interested, but the answer is no.
Thank you.
Yes, Diane.
Slide 19.
19, you got it. This seems.
You provided evidence in the migration of the pit.
Yes.
And I'm interested in the the asymmetry in the changes of the slope. So you see that one maintains its sharp face, the right-hand side, and the left-hand side doesn't. There was some work done by the Danish looking at trench infilling in response to oblique currents, and they showed evidence of these helical vortices that were generated along the walls that would either maintain the slope or diffuse the slope. Have you looked at that at all?
So I got very lost in that whole world because the original model that kind of predicted the way this dredge pit would infill was actually developed by the Danish and was based on kind of the concept behind the one-dimensional model was basically that the dredge pit would infill with its orientation to longshore current because the entire shoal is migrating landward. So basically you would start to have the pit infill because the shoal is migrating and it would just kind of get eaten up from the east side towards the west side. So I did get lost in the literature a good bit about kind of the wave action and the kind of current action that happens in here. I do think that those types of things did play a role, right? We've got kind of a specific orientation for longshore current, and I do think those types of things definitely played a role in shaping the way sediments either collapsed or maintained.
Curious, is CPRA doing long-term monitoring of this resource, or is this just a one-off study?
No, it's not. It's mostly BOEM that's funding these types of projects. So BOEM and oh, I just blanked. There's a whole Gulf Coast network of geomorphologists that are doing this type of work. But like Caminata that I showed you on there originally, Ship Shoal, Caminata, Block 88, Raccoon Island, like there's a bunch of dredge pits out there that are being actively monitored. There's a whole series of literature that I'd be happy to share with you about them. But yeah, this is a long-term ongoing thing that they're still working through. And actually, so I gave this presentation to them and they're like, oh, so hurricanes. And I said, yeah, for sure. They said, great, let's go do another survey. And I have not been involved with that. My dissertation advisor is taking that off with a new student, but that's something that they're very interested in. Yes.
I'm just curious if there's a reasoning for like the shape of the dredge pit.
So that's a very good question. The original engineered design was very different, and I don't know why they came up with that specific design, and I don't actually know why it wound up being this. That's also another reason that the initial model didn't work. The dredge pit that they modeled wasn't what they wound up with. So that's not really fair either. It's a whole lot of non-direct comparisons. But I do not know why this shape was chosen. It's also kind of odd, this particular dredge pit, that northern edge is actually right at the very tip of Ship Shoal. So it is right on that crest. So it is one of the more shallow dredge pits, so it's impacted by the wave base a lot. But it also means that that northern edge isn't very stable because it's already on a crest, right? If you think about the way sand migrates, it's migrating landward, we're already on that crest and we're kind of slumping down that backside anyways. So there's a lot of interesting, what I would consider design choices for this particular project that I don't know the origin of. Yes.
Bit out of left field.
Okay.
Maybe a stupid question. But you mentioned that you studied the last 10,000 years of geology in the
Yeah.
West, and Mississippi has switched delta a few times in that time. How representative is that location for an average location of the coast? Does it matter whether it's in a recent location where the delta used to be? Is the composition of the sediment different?
So the reason
Transport different? Or is it all the same across?
The reason I kind of brought that up initially was to kind of give you an idea of the type of material, like why they were dredging that particular shoal. It was a beach system, so that's kind of why I put that thought in your head. But this is pretty representative of Louisiana, right? It's a very unique system with many abandoned delta systems, but this is pretty representative of Louisiana itself. Now, if you get to the eastern side of that Birdfoot Delta, kind of towards the Alabama side of things, it changes dramatically because that longshore current is coming across from the east to the west. but for a majority of Louisiana and parts of like Texas this is very representative.
And again, pardon my ignorance, but there's no spot where you can say, okay, here is what the delta used to be 1,000 years ago. It looks very different with regards to composition versus further over.
So let's see, if we go back to this map here, this is kind of the established names, locations, and rough ages of different Mississippi Delta, like major delta building events. Now, this is not all of the delta system, right? This only goes back to 46,000 years. Mississippi's been around a hot minute. I'm sorry, 4,600 years. Some of the earlier systems, like this Atchafalaya Bay system here, that's going to be one of the earlier systems, the older systems, has lost most of this kind of submarine shoal systems, but it's also the current kind of not main output. It's one of the current outputs for Mississippi Delta. So I'm not going to remember the date, but basically they had a flooding event where they lost part of the levee, and it's basically split from the main draw down the main Birdfoot Delta, and we have a new delta forming kind of to the west where that Atchafalaya Bay basin was. So basically it's that Penland cycle that I was talking about where things start to reoccupy original spaces. So for the most part, all of this fits well into this system, which is specifically designed for the Mississippi Delta system.
You mentioned some reasons why the model didn't predict well.
Yes.
There's
a lot.
Well, is 3.5 times. That's pretty poor for any sort of model. Is there any experience of using that model where it didn't do a good job of predicting what was happening?
So I think,
Or should we just be concerned about that model in general?
so it's really hard. I think that model did a lot of really good legwork of figuring out some base inputs. There's some really good inputs that I think are very applicable and very reasonable to continue to use. But I think that because it's a simple 1D model that's looking at kind of the migration of the larger system as the way that this particular dredge bit is infilling, I don't think that's accurate. When I start to really look at the repeat bathymetry, the constant rate of migration for that shoal doesn't seem to hold up year to year. Long term, 10 years, 20 years, 50 years, it applies.
Yeah.
Short term, year to year, it doesn't seem to apply. And I think that part of the reason it doesn't apply short term is that the Gulf experiences these episodic crazy storm seasons and creates major change that kind of gets smoothed out over long term.
So it's kind of like the difference between climate and weather.
Yes.
So
Yes, it's a very good way
it'd be
to-
a much better climate model than it is a weather model.
Exactly,
It is
exactly.
weather.
So yeah, so there are a couple, I was talking to Diane about kind of looking into all those different modeling systems the Danish have put out. They've got some really great nitty-gritty detail ones. And I think what needs to happen, and I am not the person to do this, is to combine that large scale migration model with the small scale kind of vortices model. And I think that that's something that needs to be done. And I think it would be able to be that weather prediction.
So it gives you something with more skill to.
Yeah. And that is something that at the end of this paper, I explicitly say, someone should do this. That is a little bit outside of kind of my things more the mapping and kind of the conceptual things. Anyone else?
There are no more questions. Let's thank Kelli again.